Okay, so we've seen that for many reactions, collisions are required between the reactants in order to give products, in order to have that reaction. And so this is a central factor which affects the rate of reactions. You see, if you know that if you were to increase the reactant concentration, you would have more collisions then per second or minute. Having more particles within a container makes it much more likely that they'll collide. So, for example, if we have 4 particles here instead of those 2, we're about twice as likely to have to collide in a given minute. And so, having then more collisions, we have a greater rate because those collisions are required for a reaction to occur. Similarly, changing the particle size can change the rate. For example, let's say that you were burning carbon or coal. This solid reacts with gaseous oxygen to produce a gaseous carbon dioxide. Now, what would react faster? One big chunk of coal, or that coal broken up into coal dust, extremely small particles of the same mass as before, but just much, much, much smaller. Many more particles, but much smaller. Well, as you decrease the particle size, as you break that big chunk into many small chunks, you will be increasing the surface area, the area over which that oxygen gas comes into contact with that solid carbon. This surface area is only so much in that big chunk, but it's much, much greater if you have dust of it. So by decreasing particle size, you increase surface area, hence you increase the number of collisions that might occur in a given minute between a gas and a solid, say, and therefore you increase the rate. And so you can find that coal dust or other dusts, for example, in storing crops, can be extremely explosive compared to the solids themselves. Now, changing temperature also affects rate. If you increase the temperature, you will increase the average kinetic energy of your particles, and hence, when those particles collide, they'll have greater speeds and therefore greater kinetic energies and greater kinetic energy turned into potential energy. And we'll see in a moment that that results in a greater rate because of the increasing proportion of those collisions, which result in reaction. And finally, adding a catalyst to a reaction can increase the proportion of the collisions which result in a reaction as well, and hence that will increase the rate of the reaction. So we can investigate all of this using this diagram, potential energy versus reaction progression diagram for a reaction. So consider that you have some reactants, A and B. A and B, they react when they collide, they combine, and react into C. So A and B, our reactants, they, as we go to the right, as we have greater reaction progression, they turn into C, our product. Now, in order to do that, they have to go from a fairly stable state into a very unstable state, in which we have these particles in an unstable state where the particles might be arranged in non-ideal ways, high energy ways. This is called the transition state. So we can represent this by, in this case, AB with this double cross in the top right corner. This is also known as the activated complex. And because it is so high in energy, you have to add a lot of energy to your reactants when they collide in order to get to this activated state, and hence then also go and turn into products. This amount of energy that is needed is called the activation energy, EA. The amount of energy that you need to convert from kinetic energy into potential energy. So what might happen is A and B, they might be moving along and they might then collide with each other. Now, when they collide with each other, they had speed of motion, they had kinetic energy, but that kinetic energy is turned into potential energy. And then as they collide, as they get closer and closer together, that kinetic energy turns into potential energy and the reaction proceeds. Although in many cases, there is not enough kinetic energy and therefore not enough potential energy for the reaction to proceed all the way. And so instead, it will go back into its original form, in which A and B might then bounce off of each other and no reaction occurred. But in some cases, A and B might collide and they might have such a high amount of kinetic energy that that kinetic energy turns into potential energy greater than the activation energy needed, and then the reaction can proceed. And so A and B turn into that product by going through that activated complex. Now, many reactions, they might make it up to yay point and then they roll back down, etc. And so it's important to increase reaction rate. You have to have higher average kinetic energy for your particles, because then instead of many particles just making it up to this point, they might actually make it with just a little bit more kinetic energy, make it over the hump here, the barrier. Now, this activation energy is defined as the minimum energy required to initiate the reaction. It's in kilojoules per mole. This reaction, you see, had a lower potential energy for the product than the reactants. There was a loss in potential energy and enthalpy, and so we could say that heat was released. This was an exothermic reaction. But in other cases, for example, where there's a higher potential energy for the product than the reactant, that would mean that a certain amount of energy and enthalpy is absorbed by your particles, and hence you have an endothermic reaction. Now, we mentioned here that the amount of kinetic energy and hence potential energy resulting from that is essential to the reaction rate. We can describe this using the following diagram, where you can see that there are a certain number of collisions with certain energies. So let's say that you're at T1, temperature 1, and let's consider that temperature 1 is less than temperature 2. So it's colder when you're at temperature 1 than temperature 2. If you're at this cold temperature, your particles might have certain low kinetic energies, or they might have high kinetic energies, but overall they'll tend to have kinetic energies which are about the same as all of those other particles in the container. Now, the kinetic energies, when these collisions occur, can turn into potential energy, and sometimes you'll have low potential energy. Sometimes the amount of potential energy gained from the collision is high, but most of the time it will be in the middle. But occasionally those collisions will give enough potential energy to make it over the activation energy barrier. There will be that minimum amount of potential energy to react. So there will be some small proportion of your particles which collided reacting. The proportion of your particles colliding here is quite small. Only some small amount, some small area of this curve is or has at least the minimum energy needed to react. Whereas most particles, their they had less potential energy needed to react, and therefore when they collide, they do not actually react. But if we increase the temperature, if we have a higher temperature, then we shift this graph and this curve to the right. Shifting to the right, because having a higher temperature gives us higher average kinetic energy, and therefore more particles when they collide will have that minimum kinetic energy. Shifting to the right at this higher temperature gives us a much greater proportion of collisions which actually result in reaction. In fact, you can see here that perhaps by increasing the temperature only by maybe 30 or 40 degrees, the proportion of particles reacting actually has increased dramatically. Whereas previously it might have been, say, 5% of particles. Now it might be about 40% of particles which react when they collide. Having small changes in the temperature can have dramatic changes in the reaction rate. Now, this is due not to an increase in the number of collisions from having higher temperature. Not really. This is a negligible effect. The real reason that increasing temperature increases rate is because there's a greater proportion of particles which collide with the right kinetic energy. And so we can kind of take a look and describe all of this using the Arrhenius equation. Now, if you're in my AP chemistry class or regular chemistry class, you don't actually have to use this equation, but you should be familiar with it if you're in AP. This relates the rate constant, and hence the rate, versus the collision factor, the activation energy, the rate constant, and temperature. It basically describes that if you increase the temperature by about 10 degrees Celsius or Kelvin, you'll oftentimes double the rate or so. Big effects. All right, thanks for watching, guys.